Hello everyone, my name is Ritik Majumdar. I am working under the supervision of Professor Anurag Kumar and Professor Rajesh Sundarasan. The title of my project, MTech project, is a comparison of scheduling algorithms for packet voice in 5G cellular system and their impact on full buffer EMBB flows. This work was presented at NCC 2025 in IIT Delhi. So let us consider a scenario where we have both real-time and non-real-time queues in the base station, and the base station has to serve both. Let's take an example of UNR flows as an example of real-time flows, and EMBB flows as an example of non-real-time flows. Now, the incoming traffic of VNR flows is characterized by alternate active and silence periods. During active period, a burst of packets arrive with an interval time of 20 milliseconds, while during the silence periods, no packets arrive. And the EMBB flows are considered to be infinite backlog or full buffered. Now, the QoS requirement of a VNR flow is that each VNR packet after arriving must be scheduling within 20 milliseconds or 40 slots, considering 0.5 millisecond per slot. That is before the arrival of the next packet. And the QoS requirement of the EMBB flows is that it requires maximum throughput. Now allocating VNR flow. Now allocating resources from the resource grid to VNR flows will reduce the throughput of the EMBB user, especially if done in a suboptimal way. So how the scheduling is done in current LT and NR systems? Semi-persistent scheduling is used to schedule voice packets. That is, some fixed resources are allocated in periodic intervals to the voice packets. This does not exploit the channel conditions, and also it does not exploit the multi-slot deadline that we have. But the advantage is it reduces control signaling and also saves UV power. So in this scenario, the objective of an optimal scheduler is to minimize the resources used by the VNR flows and to maximize MBB throughput. So in our work, we have considered the following assumptions. The first one is the channel is considered to be IID across slots as well as UVs. The transmission rates are considered to be the same as the Shannon capacity in that slot instead of discrete MCSs. And we have considered a layered heuristic for scheduling. That is, in the beginning of a slot, we prioritize scheduling VNR packets, and after we are done with scheduling VNR packets, we provide the rest of the resources to EMBB flows, which are scheduled by a gradient scheduler. So we have considered four scheduling approaches. The first one is schedule on arrival. This is a simplified form of semi-persistent scheduling, which is popular in the industry, where we schedule a packet in the same slot in which it arrives, without taking advantage of the channel as well as the multi-slot deadline, as said before. Then we have the Gini Idiot scheduling. This is a non-causal approach which provides an upper bound to the MBA performance. So in this scheduling method, on arrival of a voice packet, we assume that we have perfect knowledge of the channel condition in the next 40 slots, and then we schedule the packet in the slot where the channel condition is most favorable. Then we have the optimal stopping time policy. Here we formulate the scheduling problem as a finite horizon MDP. We define the cost of scheduling a packet in each slot for all the 40 slots, and then try to minimize the costs over all the slots. So it turns out this yields a threshold policy, and where we have optimal thresholds in each slot. So this is the expression of the thresholds, and the scheduling is as follows: that we schedule a packet in a particular slot if the channel quality exceeds this threshold. This is also difficult to implement practically because we require the channel statistics for implementing. Then we also have proposed a heuristic, which is the rate to deadline ratio. The rate to deadline ratio is a heuristic index which is RK by delta K minus 1, where RK is the channel quality in the kth slot and delta K is the residual deadline of the packet. So if this index exceeds a particular heuristic threshold, then we schedule the packet in that slot, otherwise we defer it to the next slot. This is easy to implement as it does not require any channel statistics. So in our simulations, we have considered the following simulation parameter as shown in the table, and this is the distribution of the UVs that we have considered. So a rate region is a set of all rates that can be achieved by any scheduling policy. So for our performance metrics, we have seen that how much this rate region for the EMBP flows shrinks for the different scheduling policies. We also consider how much the average amount of resources were used up by the VNR flows and also the voice packet drop probabilities. So this plot shows the different rate regions for different scheduling policies. The outermost blue line is the EMBP rate region for when there is no when there are no VNR flows when there are no VNR flows, which is followed by the red curve, which corresponds to the Gini-aided scheduling. And then it is followed by the optimal stopping time policy, and then by the rate to deadline ratio, and finally the worst performing one is the SOA, that is the schedule on arrival. We see that the optimal stopping time policy gets pretty close to the GAS, which is the best that we can get, and also the heuristic is not falling far behind. Uh, So one thing to keep in mind is this improvement from SOA to OST, that is the optimal stopping time, comes at a cost that the UV radio needs to be kept awake for all the 40 slots, uh, which leads to increased power consumption. So this table shows the percentage of the slots used by the VNR flows. As you can see that with SOA, the percentage of slots used up by the calls is very high, and which reduces drastically when using RDR and OST. And this is the packet drop probabilities, where we see that in SOA the packet drop is very high, whereas in RDR, OST and GSS is almost negligible. So now we will explore how can we improve this condition where the UV radios needs to be kept awake for 40 slots. So what we have done is instead of running the optimal stopping time algorithm for all the delta slots, that is 40 slots, we have restricted the algorithm to run for some delta dash slots. So here delta dash would be less than delta. So in this scenario, the UV radio can sleep for delta minus delta slots, which leads to power savings. So these are the rate regions. So all these rate regions correspond to the optimal stopping time policy, with some which when the algorithm is run for some restricted deadlines. So if we restrict the deadline to one, it means nothing but the schedule and arrival policy. So we see that the rate region has shrunk by a significant amount, and we see that even on changing delta dash equal to 1 to delta dash equal to 2, we see a huge improvement, and we see that the improvement decreases as we keep on increasing delta dash equal to 40. So this figure also shows the percentage of slot used by the VNR flows versus the packet versus the restricted packet deadline. So we see that after 25 slots, the percentage of the slot used by the VNR is not decreasing by a large amount. So we can see that there is a trade-off between UV power savings and the performance of the EMBP. We have also explored the correlated channels to some extent. We have considered two scenarios where The channel is not IID, but it is it has a coherence period of 5 milliseconds and 10 milliseconds. And we see that in this plot, this plot corresponds to the EMBB flows rate region for 5 millisecond coherence time, and this plot shows the EMBB flow rate regions of the EMBB flows for 10 millisecond coherence time. We see that the performance decreases, or the EMBB rate region shrinks by a little more amount on increasing the coherence time. This is because we again do not exploit the channel, because increasing coherence time leads to the reduced opportunity to explore channel variability. Thank you.